So we were looking at contraction semigroups in Hilbert spaces, and we found that the infinitesimal generators were precisely the maximal dissipative operators. Of this we said there are two important classes, and the first one we were looking at was when A, the infinitesimal generator, was also self-adjoint. So here is a very nice theorem which we prove. So let V be a real Hilbert space. Let A be a maximal dissipative self-adjoint operator on V, then given u0 in V, there exists a unique solution to the initial value problem. U dash t equals A of ut, t positive, u of 0 equal to u0, such that u belongs to C of 0 infinity with values in V intersection C1 of 0 infinity with values in B and intersection C 0 infinity with values in D. Further, for all t positive, we have norm of u of t is less than or equal to norm of u0, and norm of u dash of t is less than or equal to 1 by t times norm of u0. Okay. So this is the theorem. So the important thing to note is that so far we have been saying we can solve this initial value problem provided the initial data is in the domain of A. Then otherwise we called it a generalized solution, but then here we, in the self-adjoint maximal dissipative case in a Hilbert space, you can solve the problem classically even for any data in the entire space. The only price you pay for that is that you lose continuity at t equal to 0. That was the only difference. Previously we had C1 of closed 0 infinity with values in V, C of closed 0 infinity with values in dA, but now we have C of closed 0 infinity with values in V, but C1 of open 0 infinity with values in V and C of open 0 infinity with values in dA. Obviously at 0 it is not in dA necessarily. Okay, so this is a very beautiful result, namely you can solve for any initial data irrespective, you do not have to worry about it being in the domain, okay, and you lose continuity at t equal to 0, which is not a big deal. Okay, so proof. So first step is uniqueness. So let u1 and u2 be two solutions, and you write phi of t equals norm of u1t minus u2t square. Okay, then phi t is greater or equal to 0, phi of 0 is equal to 0 because the initial value is the same, and also you have that u1 dash t minus u2 dash t equals a of u1 t minus u2 t. Now you take the inner product with u1 minus u2, so that will be 1/2 of d by dt. We have seen this norm of u1t minus u2t square is equal to a of u1t minus u2t, u1t minus u2t, and that by the maximal by the dissipativity is less than or equal to 0. So phi is non-zero, phi of 0 is 0 and phi is decreasing because norm of d by dt is less than or equal to 0. So, this implies that phi is identically equal to 0, that is u1t equals u2t for all t positive. Okay, so that proves the uniqueness of the solution in this case. Okay, so step 2. Let u0 belong to d of a square. So, we are going, we said we are going to prove things in for u0 in V, but we start with u0 in d of a square, which is very smooth. So, that solution exists classical sense. That means even you have even continuity at the origin, much more than that. So, ST t greater than or equal to 0 semi group of contractions generated by A. Then of course you know that ut is nothing but st of u0. Okay. So, A lambda Yoshida approximation of A lambda positive. Okay. Then you have, let us take u lambda dash t equals A lambda u lambda t positive, and u lambda of 0 is same as same initial value u0. Okay. Then we have seen that of course u lambda t goes to u of t, and also u lambda dashed of t goes to u dashed of t. This was one of the last theorems which we proved when in the general Hill-Yoshida case uniformly on bounded intervals as lambda tends to infinity. Now, A lambda belongs to L of V, it is a bounded linear operator, and therefore we can apply the theorem which we proved, the proposition which I proved last in the previous lecture, namely, so this implies that norm of u lambda dash t, and this is self-adjoint. This also be proved. So, the norm of u lambda dash t is less than or equal to 1 by t norm u0 for all t positive. This we proved last time. So, we pass to the limit as lambda tends to infinity, and we get, you get norm u dash t is less than or equal to 1 by t norm u0 for all t positive. Okay, so this is, of course, you assume that u is in u0 is in d of a square. So now we have to do a density argument. Step 3. Okay, so we have u0 in V. Okay, then d of a dense in V, and d of a square dense in d of a. This also we saw. Now, what is the, we have DFA has the graph norm, therefore, it is continuously included in V, and DFA square is dense here. Therefore, by the continuity of this, this implies that DFA square is dense in V as well. Consequently, let us take UN0 in DFA square, UN0 going to U0 in V. So, UNT equals A of UNT, UN0 equals UN0, okay, and then we know that norm of UNT minus UMT is, because you have a dissipative operator, we know that the norm is always less than or equal to initial value. So, you have UN0 minus UM0 t greater than or equal to 0, and norm of UN dash t minus UM is again less than or equal to 1 by t times norm of un0 minus um0 t positive. Okay. Now, the first one is just comes from the fact you have this contraction semi group, and also S norm of St is less than or equal to 1. Okay, norm of St is less than or equal to 1. And the second one comes from step 2. Okay. So, then you have that u and t converges to u of t uniformly, because this is uniformly Cauchy, and u n dash t uniformly Cauchy on bounded intervals. And therefore, you know, if the derivative converges uniformly and the function even converges at one point, you know that the limit of the should be differentiable, and it should be the limit of this, implies that u of t is C1 of delta infinity for all delta positive, and u of un dash t goes to u dash t uniformly on delta infinity for all delta positive. So, what does this? So, this implies that u of t, or u belongs to C of 0 infinity with values in V intersection C1 of open 0 infinity with values in V. Okay. So, now step 4, you have to show that u is the solution of the equation which we want. Okay. So, u0 equals limit of un0, that we know, and unt and aunt converge for t positive. This implies that ut belongs to D of A, and A of unt converges to A of ut. But A of unt is un dash t, and that C converges to u dash t. Therefore, we have that u dash t equals A of ut for all t positive, u of t belongs to domain of A, and therefore, you have u belongs to C of 0 infinity with values in dA. So, that proves all the continuity properties that u is a solution. We have produced a solution for the equation. So, finally, step 5. So, un st is a contraction semi group. So, un of t in norm is less than or equal to norm of un0, and this implies that norm of ut is less than or equal to norm of u0. Okay. And for all t greater or equal to 0. Okay. And you have that norm of un dash t, because un0 is in d of a square, is less than or equal to 1 by t norm of un0 t positive, and therefore, for if you pass to the limit, that norm of u dash t is less than 1 by t times norm of u0 for all t positive. Okay, and this completes the proof of this theorem. Okay, so we will conclude the self-adjoint case, that actually we have much more to say in this. So, the self-adjoint case is a very smooth, it is a regularizing effect. So, regularity result. So, theorem V real Hilbert, A maximal dissipative self-adjoint. Then if U solution of U dash t equals A of U of t for t positive, U of 0 equals U0 in V, okay, then U actually belongs to Ck of 0 infinity with values in d of a power L for all positive integers k and L. Okay, so this is a really wonderful result. I won't prove it, you can find the proof in the book Topics in Functional Analysis Applications. Not a very long proof, but I do not want to get into it here. And so you see, however rough the initial data is, namely it is just in V, U, I told you D of AL is a space of very smooth functions. So, U belongs to D of AL for any L. So, it is in fact like if you think of Sobolev spaces, this will be something by the Sobolev inclusion theorem, something like C infinity. And in time also it is C infinity as long as you do not go to the origin t equal to 0. So, it is Ck of 0 infinity for all k. So, the solution is extremely smooth, and in the case of the self-adjoint operators. So, that is about self-adjoint case. So, now I will not as I said give a proof of this. So, let us save some time. So, now I want to go to, so now we want to look at the case when, so case 2, A and minus A are both maximal dissipative. Okay, so in this case you have AVV should be greater or equal to 0 and AVV should also be less than or equal to 0 because both A and minus A are dissipative. That means this is AVV equal to 0 for all V in DFA. Okay, so now we have a theorem. So this is a different kind of theorem. So V Hilbert space, real of course, A dA contained in V to V, a linear operator such that A and minus A are maximal dissipative. Then together they generate a group of isometries. So, proof. So, the norm of the solution will not change at all. Okay, so that is why you have an isometry. So, let S plus minus t greater than or equal to 0 be the semi groups, contraction of course, generated by plus or minus A. Okay. So, let U naught belong to D of A and ut be equal to S plus T U0. So, then you have that A of U dash T equal U dash T equals A of U T, T positive, U of 0 equals U naught. Okay, this is the solution to this equation. Now, norm of, so you take the scalar product of this equation with u of t, and then you get 1/2 of d by dt norm ut square. We have seen this before, a of ut, and that is 0, and this means that norm of ut equals norm of u0 for all t. Okay. Now, this is true for all u naught in dA, but dA is dense in V, and therefore this implies that norm of ut. Okay, so but what is norm of st of u naught is this, and this implies that norm of st of u equal to norm u for all u in V. Okay. So, the norm of st is less than or equal to 1, and dA is dense in V, and therefore you have this, and therefore S plus T isometry for all t greater or equal to 0. For t equals 0, it is just the identity map. So, in the same way, similarly, S minus t is an isometry for all t greater or equal to 0. Okay. So, now let ut equals st of u naught in dA, and you define Vt equals u of t naught minus t. For t belonging to 0 t naught. T naught is some fixed, so let t naught greater or equal to 0. Okay, so then you do this, and then what do you get? You have that v dash t, if you differentiate, this is equal to minus u dash t naught minus t, which is equal to minus a of u of t naught minus t by definition, and therefore this is equal to minus a of Vt. So, v dash t equals minus a of Vt, v of 0 is equal to what? V of 0 is equal to u of t naught. This implies that v of t equals s minus t of u of t naught, okay, and that is equal to s minus t of s plus t t naught of u 0. Okay. So, in particular, v of t naught equals s minus t naught s plus t naught u naught. But what is v of t naught? V of t naught from the definition is nothing but u of 0. So, this implies that s minus t naught s plus t naught equal to u naught for of u naught, sorry, for all u naught in dA implies by density again for all u naught in V. Similarly, s plus t naught s minus t naught is also equal to the identity map. Therefore, if you define, so define s of t equals s plus of t for t positive, s minus t if s minus of minus t, sorry, for t less than or equal to 0. Then you have ST inverse equals SF minus t, and so we have a group of isometries. So, in this case we can solve the equation backwards and forwards, because you have a group of isometries and also you have a conservation property, namely the norm of the initial value, initial data is preserved throughout the flow. Okay, so these are the important properties of these. So, we have these two particular cases, and now our next aim is to give examples from partial differential equations of these situations, namely the self-adjoint and the case where you have a group of isometries.